So if you want to drop off, have an extra break, go get a coffee, then yeah, I'd recommend that. But there were two things that people have been talking about throughout the sessions quite a lot, that I thought we could do a quick 5 minute, 10 minute demo on. One's Shiny, so Shiny always comes up and people are always interested in it. Looks kind of cool. The other one is some of the stuff that Aaron mentioned earlier around time dependency and building these markov models, and that came up just now. So Dawn just had a question there about how tricky it can be when you have a kind of almost like a black box, a tool that you're using, and learning how to do things bespoke can be valuable. So I'm happy to talk about either of these or neither. So I guess maybe I'll put in the chat, or I'll ask somebody to put in the chat if someone could just type in Shiny and Markov model, and then if you want 5 minutes on Shiny, then put thumbs up on that. If you want 5 minutes on Markov model, thumbs up on that. And if people don't want anything, then yeah, then we'll just have an extra break. I'm just seeing the chat now. Oh, there we go. Thank you. Oh, Markov's winning. Okay. Okay, that's pretty decisive. That's pretty decisive victory for Markov modeling. Okay. So what I'll do is my prediction was that everyone was going to want Shiny, so I'm quite surprised. So I'll switch over to state transition modeling. And so this is gonna just pull over. So what we're going to do is go through a paper or a bit of code that's been adapted from a paper originally from the Darth group and Aline Krijkamp, who presented on Friday. And they have some really nice stuff around building Markov models, and I'd really recommend checking out that paper. I'll link the paper in the chat after this. But essentially, it's a 4-state Markov model where you have healthy, sick, sicker, and dead. And so we've used that throughout our courses on working with Shiny and other things. And so we've used that in a number of open source, open access papers. And we find it's a nice teaching model. And so what I thought it might be quite useful to go through today is not only the little interesting bits of code that Aaron mentioned earlier about moving through an array for time dependence in a model, and how you do that. So what I'm going to do is just assume that we don't have time to go through all of the different parameter inputs. So I'm just going to load them all, and we're going to get to the point where we have a single matrix for transition probabilities. So in this case, we have a matrix, and that matrix here, which you can see in the bottom left, is just full of NA values. And so we're looking at the transition probabilities between, let me make this larger, the transition probabilities between being healthy and moving to healthy, sick, sicker, or dead. And so this is a standard transition probability matrix, and we can fill that in with the parameter values and check that the rows all sum up to 1, and they do. And so now we've got this new transition probability matrix. And so this is great if we want to assume that we have probabilities that remain constant throughout our entire simulation. So the probability of becoming sick or sicker or dying is the same in the first cycle as it is in the last cycle. And so we can construct a Markov trace, again using a matrix. And then we can look at the first 6 rows of that and fill in the first row. And here we're just going to assume everybody, 100% of the cohort there is healthy. So if we look at those first 6 rows, which, there we go, we have everyone, or 100% of the cohort, healthy state. And so this is the bit where it's really, really nice to see in R. Let's just run a single cycle. So let's take that first cycle for the cohort and multiply it with a matrix multiplication. So we've got our percentage sign, multiply percentage sign, multiplied by our matrix. And we have to make sure that these are compatible. So the length of the vector here is length 4, has to be equivalent to the the number of rows of the matrix here, and then we'll perform this matrix multiplication and fill in the second row. So you can see we've indexed here the second row. And so if I look just at row 1 and 2, you can now see that we've got 100% healthy in the first cycle, which is what we initialized with, and then we have our proportions filled in this second cycle. And so we can just follow this exact same process, but through for all of the cycles from cycle 2 to cycle n_t, which is the number of cycles in the model. And so essentially our simulation in R is just one line of code wrapped into a loop. And so we run that, and there we go. We now have a full trace. And so we can do a base R plot just to show broadly what that looks like. We've got the population that are healthy decreasing and the population that are dead increasing, of course, as we'd expect. And so the question then becomes, that is a massive oversimplification. How do we go about adding in time-dependent transition probabilities? So what I've done here at the start of the script is remove everything. And then what I've done is source the script before so that we have all of the parameter values from before. And then I'm just reinitializing the trace because we'd filled it in with these values. And so now you can see we're back to where we started. We have all the same parameter values and an empty trace. So again, 100% of the cohort is in a healthy state. And what I'm going to do now is rather than create a matrix of transition probabilities, I'm going to create an array of transition probabilities. And this extends the number of dimensions, as Aaron mentioned before, from 2 to 3. So now we have the same dimensions as the original matrix that we had. So we have a 4x4, plus we have this extra time dimension, which is 30. So our array is 4 rows, 4 columns, and 30 what I call slices. Aaron loves cheese, so I don't know what you refer to that as, like, I guess cheese slices. So we've got a 40 by 40 by 30 3-dimensional array. And for those coming from Excel, this confuses the hell out of everybody because Excel doesn't operate like this. It operates in spreadsheets, in workbooks, and specific tabs. And so now we have this array. We can then see that we have each cycle, and each cycle at the moment contains the exact same transition probabilities. So this is essentially the same as before. And we can run the simulation and check that we get the same outputs. And this is because we've fixed every slice of the array to have the same transition probabilities. But now in our courses, we have this example where everybody dies in cycle 4. So you imagine an Armageddon-style scenario. Asteroid hits the Earth, Bruce Willis isn't there to save us, everybody dies in cycle 4. So in cycle 4, our transition probabilities look like this. And if we reinitialize our trace and run the simulation, you can now see that what we're doing in this simulation, if I just look at t = 2 as an example, we can now see that we're going to use, in t = 2, we're going to use this transition matrix because we're subsetting our array in the 3rd dimension to extract just one transition probability matrix. But in t = 4, where are we? Sorry, t = 5, we're going to use this transition probability matrix. So everybody's going to die. So if we run that simulation, and again, this is how easy this is in R, and create the plot, we're going to see cycle 5, everyone dies. So it's just a really quick demo of how straightforward it is to build some of these Markov models in base R yourself. And so potentially thinking about whether you need to rely on a kind of external package that does a lot of this stuff under the hood very efficiently. But of course, once you've built it yourself, you have the full flexibility of being able to do anything that you like to adapt the way that this works. So if you need to have treatment switching or discontinuation or anything else built in, you can build that in yourself without a reliance there. So I've talked over for too long. If you are interested in this, please reach out, and happy to talk about this more. But James successfully filled the gap, and I've added to the scope. So yeah, thank you very much.